Okay, so it's on. Yeah, thank you for inviting me. I thought this would be a good opportunity, especially with all the ZTF people sort of abandoning me this week, to talk about moons and rings around exoplanets instead. So something a little different than I usually talk about. So trying to get into this exoplanet field, if there's anything you should do, I guess you're supposed to show this plot, right? That's kind of like you're contractually obligated to show this. So you just go to the IPAC website, and you can download this. And it's just amazing to see, how much this field has changed in the last decade or so, all these new discoveries of planets. And if we look at our solar system, we see that things like moons and rings are really ubiquitous. There's over 200 moons in our solar system. All of the gas and ice giants in our solar system have rings, right? And so it's just natural to wonder how many exoplanets also have moons and rings out of those 5,000 or so exoplanets that I was just plotting there. And it's just not this sort of idle curiosity. For example, moons in particular are really important. So for things like habitability, moons may help in stabilizing the obliquity and maybe help lead to more regular seasons and a stable climate. This is something that's been worked on by a number of people, but I especially suggest looking at Ganji Lee and Constantine's paper, where they show a nice framework for treating the changes in obliquity when you don't have a moon. Tidal interactions with the moon can prevent tidal locking to the parent star, impacting the sort of weather conditions. So, a lot of these exoplanets that we're discovering are so close to the parent star, we sort of just assume that they're all going to be tidally locked. But if you just have a moon there, that could really make a big difference in having that occur. And tidal heating from moon could also assist in providing us additional heat source for the exoplanets as well, assisting in things like plate tectonics, the carbon cycle, dynamo generation, all these things that we, at least from our experience with the Earth, think are pretty crucial for habitability. And the presence of moons or not can also provide clues about the migration history and the evolution of the planets, right? So things like how the planets had migrated can end up forcing the moons to be shed in some cases. And so finding these moons would be important clues. And then finally, for the gas giants and habitable zones, the moon itself may be able to host life, and that's maybe where we'll find life instead of necessarily on the planets, which we know well, right, from the forest moon of Endor, right? So let's start thinking about where could we expect to find these moons? So the moon itself, so if this is definitely not to scale, but here's a planet with a moon and a parent star. And right, so the moon has to be outside of the sort of Roche lobe, otherwise it's going to be tidally disrupted. And fortunately, even though the masses of these moons were not very well known, it only depends on the density to the 1/3 power. And so the density of a moon probably doesn't vary very much. And so this radius is pretty well known for a given planet. And then they can roughly exist out to the heliosphere. Beyond that, they're going to be lost to the parent star. Okay? And so it's interesting, though, when you start looking at and trying to understand where moons could be around planets, is that, we have this abundance of M-dwarfs that we're finding planets around. We're really interested in the habitable zones of these M-dwarfs. But when you have moons in these sort of situations, you're naturally in a state where the planet's going to feel a comparable tide from both the moon and the star, because you are so close to that parent star to be in the habitable zone. And so that got us thinking about the interesting dynamics that would take place in such systems. And so just to make sure everyone's on the same page, I just want to give a simplified background on how tides will work in these systems. This picture goes back to Darwin, not Charles Darwin, but his son George Darwin, when he was thinking about how the Earth and the moon interact. And right, so this is a little exaggerated, but this is how the tides, act on the Earth from the moon's gravitational pull. But of course, the moon is going around slower than the Earth is spinning. And so as the Earth is spinning, right, as the Earth is spinning, there's going to be this angle where the Earth cannot react immediately to the tides and deform, and instead it's going to be displaced by some angle. And it's going to be displaced ahead because the Earth is spinning faster than the moon's coming around. And so this angle, delta, is often parameterized by this Q factor. where this Q tells you something about the dissipation of the tides. So if you have a more dissipative tide, you can see in the denominator, then you're going to have a smaller Q, and vice versa. If it's not very dissipative, Q is going to be very large. And so what kind of values of Q do you expect for this? And so this goes back many decades, sort of estimating these values for objects in the solar system. If you have a perfect fluid where it's completely, there's no dissipation at all and it just reacts immediately, then Q is basically effectively infinite. And so just so you have some numbers in mind, so everyone's on the same page, rocky planets like the Earth, which are pretty dissipative, you have Qs around a few tens. If you have an ice giant like Neptune, it's measured to be around maybe 10 to the 4. And then gas giants like Jupiter, maybe around 10 to the 5, 10 to the 6, depending on the interactions. And so you might naturally ask yourself, when you see this sort of simple parameterization like this, is Q really constant? And so when I was putting this talk together, I was reminded of this quote from Peter Goldreich, who's unfortunately he's not here, but I think this might have been his first paper. I'm not sure, but it's a few years ago. This will be the 60th anniversary, I guess, next year. And so he says, Q will in general vary with the frequency and amplitude of the tide and the size of the sphere. In addition to its composition, in our discussions we shall use the language of linear tidal theory, but we must keep in mind that our numbers are really only parametric fits to a nonlinear problem. And so this is, good advice, but it's something that theorists like myself keep ignoring over and over again for the next basically 60 years. So that's what I'm going to do here. So anyway, the tides you have this misalignment, and because of this, there's going to be the torque that's pulling on the Earth, and because of this, now the Moon slows the planet's spin. It gets pushed away, as we know, about 4 centimeters per year, and it slows down the spin of the Earth. But now we want to consider a more complicated problem, because now we're going to have the combined tides of both the star and the Moon and how those interact together. Okay? And I don't want you guys to think, there's a lot of other people that have sort of been working on these sort of problems for exoplanet systems over the last 2 decades or so. And so I'm just contributing to some of these discussions. So with all that in mind, we can start now doing some sort of time evolutions of understanding how the orbital properties are expected to change in these systems. And so there's a lot of parameters to deal with, potentially. You can see my mouse here. So here's the period. Here's the separation of the Moon. And then this is how much tidal heating you're getting. And so given this sort of Q parameterization, you can now use this to evolve a moon planet star system forward in time and see how the period of this is the period of the planet changes with time and the separation of the Moon. In this case, I have a half solar mass star, and so to keep it in the habitable zone, it's at about 3 AU. So let's watch how this starts evolving with time. And you can see, sort of just like the Earth-Moon case, right, the planet gets spun down, it's moving, the period is increasing, right? And then the Moon's getting pushed farther away, just like our Moon is. And you can see in this case, actually, after a pretty short amount of time, less than 100 million years, the Moon's going to get lost because you end up going out beyond this hill radius, okay? And so you could say, okay, well, what's happening is the planet is donating angular momentum to the Moon, pushing it away. So if I start with a planet that's spinning a little slower, it's not going to have as much angular momentum, and then it's not going to push the Moon out as far. And so maybe I can save the Moon in those cases, right? So we can do that. And so again, you kind of reach this point, and then what happens? So you can see I saved the Moon, but I didn't save the Moon, right? So just by changing the initial period of the planet, you can see just by a little bit, okay, great, I'm able to save the Moon, but then it looks like something else catastrophic is happening here because now the separation between the Moon and planet is basically going to 0, okay? So what's happening here? Why is it looks like you can't, it's hard to keep a Moon in either case, right? And so the first thing they notice is as the period's changing, you can see it comes up and it sort of reaches this equilibrium period here for a while where it stabilizes before it starts dropping and the moon starts falling in. And so it's pretty easy to derive analytically what this equilibrium spin frequency is of the planet. And so you can see here it's just sort of this weighted average between, so this is the equilibrium spin frequency of the planet. Here is the rotation, this is the orbital frequency going around the star, this is the orbital frequency of the moon going around the planet. And so you end up with this sort of average where these are the time scales. This is the synchronization time scales with the moon. This is the synchronization time scale with the star. So you can see basically, for example, if the synchronization time with the star went to 0, you're immediately synchronized with the star, you would just become synchronized here, right? These two would be equal, and then vice versa. And so necessarily, when these taus, these time scales are roughly sort of equal, which what we're finding for M dwarfs, with planets in the habitable zone of these M dwarfs with moons, you're going to end up with an equilibrium spin frequency for your planet that's kind of somewhere on average in between these two always, right? Okay, so that's the first step. So now we want to understand, why does this moon now crash inward? And so what's happening is, right, we always have this frequency that's in between. And so what's going to happen here is you can see that the moon is always spinning faster, and so the moon wants to torque up the planet. So the moon moves closer, right, as it's torquing up the planet. But now you reach a new equilibrium spin frequency, and now again you're spinning slower than the moon's orbiting, and so you want to torque up the planet again. So it just runs away. And so you end up in this case where you always end up, if you go long enough, it's always going to be unstable. The moon always is going to fall in. But what's kind of interesting is, depending on the parameters, and it's not really fine-tuning anything, this really can vary a lot. Sometimes it happens in only a million years. Sometimes it happens in tens of billions of years, which is pretty amazing because to imagine you'd have a system that looks like it's stable for like 1 billion years or more, plenty of time to develop life, everything's going happy, but then once you hit this instability, after a while, the moon's always going to fall in like this. And so in one of our papers itself, we go through, there's a lot of parameters you could potentially change between the spin period of the planet, the separation with the moon, the masses of the star, and so forth. And so you can get a wide variety of different types of evolutions, but please look at this paper more if you want to sort of see the diversity of different types of outcomes for these moons. But in general, you can see, definitely in a lot of cases, you lose the moon pretty quickly. And then also what you can see is it's very sensitive to the initial period, the spin period of the planets, what's going to happen with these moons, the final fate of them. And so to sort of understand this in even more detail and apply it to real exoplanet systems, I worked with my grad student, Armin Takajian, who's a student at USC, and we wanted to start applying these models to real exoplanet systems. So the plan was basically take some of these real exoplanet systems that we actually know about, where we have measurements of these things, and then add hypothetical moons to these systems and actually understand, integrate these orbits forward, okay? Not just use analytic relations, actually do the full integrations and try to understand for each of these how likely are they to be able to keep their moons, okay? And the thing we found is, the composition, the properties of the planet really play a crucial role when you're doing this, right? Because a lot of these transient exoplanets that we have, the vast majority of them, of course, are from Kepler. We have radius measurements. We don't actually know what the interiors of all these things are like. And as we've seen, both the densities can vary a lot, and then even more so, the Qs can vary a lot, depending on if you have an ice giant versus a rocky planet versus something that's more like Jupiter. And so in particular, we have planets, that are down to around 2 solar masses. They could be rocky or Neptune-like. You could have things that are more like Neptune or Jupiter-like. And the Q is going to change drastically with these internal properties. And so if you are able to find moons around these things, it's going to put very strong limits on what the internal structure of these planets is like. And so sort of this, to summarize the results from this paper that Armin led, he has a lot of plots like this. I won't show them all, but it's to sort of give you a flavor of it. So this is showing how long can you actually keep a moon in gigayears. Where's my cursor? As a function of the flux, basically, this is around the habitable zone because this is a similar amount of flux that the Earth is experiencing. Of course, with these systems, we have a lot of planets that are much closer to their parent star than the Earth is. The ones that are filled are planets that we actually have mass measurements, so we know what their density is and we know what their structure's like. But a lot of them, we don't actually know, and some of them are sort of borderline. And so we actually provide different plots and different predictions for various planets that are on the border, whether we would expect them to have a moon or not, depending on what kind of internal structure they have. And sort of the upshot is we find roughly 40 habitable zone planets that would probably be able to host a moon for about a gigayear or more. And then if you aren't just fixated on the habitable zone, there's probably hundreds of more that we could find. But this number will vary depending on the composition of these planets we're finding. So, okay, this is all theoretical moons, but what about real moons? Well, we have the moons in our solar system. Those are pretty well studied. But we also have some potential exomoon detections. And so there have been at least 2 now where we think we might have seen some exomoons. These are pretty extreme, different exomoons than maybe what we know about from our solar system, because in each case, you have something that's like, roughly a Jupiter or much larger sized planet. And then you have an exomoon that's more like a Neptune than a rocky exomoon like you kind of know and love from our solar system. So, they're very different, but can we apply the same principles that we're discussing for these other exomoons to this case? And so that's what we did, is we basically said, okay, given that we have the properties of these exomoons, we know this moon had to start somewhere, and then it's going to tidally evolve with its planet. And so that's what we did. And then we looked at, for a given Q, how long does it take to migrate to the position that we see it at now? Okay. And so these different solid lines are basically the different Q values we considered. And then these are the migration times you need to get to, for a given initial separation, to get to the separation that you have now. And this is in units of the Roche radius of the planet. And then, so given the age that we know for these systems, measured for the star, we can now predict what the Q needs to be for each of these planets. And you can see, actually, for these sort of Jupiter-ish planets, we get something that's in the range of, 10 to the 5 or so. And so maybe, it's not crazy. It's not, if I got something like 10 to the 3 or some really weird number for these Jupiters, of course I'd be surprised, right? But at least it's showing in principle that this sort of analysis it could be effective for understanding the structure of these planets. Now, one thing that is interesting is, these things are still tentative, and there are different solutions for the position of these moons. So, for example, for 1625, there are some arguments that the moon's actually roughly twice as far away from some of the solutions. Now, if that's the case, then the tides really shouldn't act at all in that case, and you can't really put any limits in Q if that's really true. But then that also is kind of interesting, because that would say that now we have one very extreme Neptune-sized moon in Kepler 1708 that's under the influence of tides, whereas we have one that's completely different, and it really implies maybe even a different formation mechanism, even though they're kind of similar systems. So either way, there's an interesting sort of mystery there. And hopefully, as we find more exomoons and also nail down the properties of these ones, we can actually do this sort of analysis even better. And where I think this would be especially exciting, but this is very far off in the future, is, of course, right, there's this very well-known plot now showing the planet size versus the number of planets per star, and we see this gap here in the radius distribution between the sort of Earths and super-Earths and the sub-Neptunes. And so, at this overlap region, presumably there's going to be rocky planets and non-rocky planets, I would think. It's not going to just be, distinct. And so if we could start finding moons, especially around some range like this, it would be a really amazing diagnostic to determine between the different types of structures you might have when these sort of different types of planets are overlapping in radius space. Okay. And so how would you find more of these moons? So we've also been thinking about that. And so in particular, a really great example is the Io system in Jupiter, right? In these cases, we have moons and resonances. And so motivated by that, we started looking at resonance groups of moons around different exoplanets. And so this is just an M-body simulation we did. It's just in the frame of showing, this is just a moon being perturbed around a planet. So there's another moon that's out further, a longer period, but they're in resonance. And so the point is just that you can see that the orbit is kind of gyrating around. And that's eccentricity that's being driven by the resonance between the different moons. Okay. So in analogy with the solar system moon systems, we expect many moons may be in resonances and for exoplanets as well. And these resonances can drive eccentricity and maybe heat these exomoons to even be more detectable than maybe we thought before. And so different ways you might be able to heat them. Well, so using these M-body simulations and also semi-analytic analysis of these resonances, we have some predictions for how heated you could get these exomoons in some of these systems that we've been seeing. And I won't go through the details, but the upshot is you can get some of these heated up to many hundreds of Kelvin. And then they would be very bright, and you potentially could see these things through various ways I'll talk about in the next slide. But the issue is that we looked at in this paper is you get a resonance, you heat, the orbit decays, but then because you also have these tidal interactions, you get pushed back into resonance again. And so through this, this push and pull between the resonances and the tidal interactions with the parent planet, you're able to get an equilibrium heating rate that you can predict, that you would expect these multi-moon systems to have. And so kind of the two ways we've been exploring that you'd potentially be able to actually detect these is in secondary eclipses. Now you'd have this extra hot moon, and if you had detections at around the 5 micron range, you would be able to see, where's my cursor? Here you go. You would be able to see this excess from this hot moon that's contributing to the emission. Or potentially kind of an analogy with Io, as you heat the moon, you're going to produce volcanic species, things like sodium and potassium, that are going to produce a cloud in front of your exoplanet that you can see through transit spectroscopy. And so this was a nice idea that Oza had. He's, I believe, a postdoc over at JPL now, of a way to also detect these exoplanets. I mean, these heated exomoons. All right, so we've been talking a lot about moons so far. My title also had rings in it, so where did the rings come up? So this comes back to this question of a lot of these moons are actually being destroyed, right? And so what do you expect to happen to these exomoons? So in some cases, right, the moon gets pushed out beyond the hill radius, and it gets lost to the planet. And so there was actually a nice paper from Brad Hansen that was posted just in the last few weeks, I think, where he shows that because these moons still have memory of the planet that they were with, they still are in that sort of same system, and they actually, even if they're lost beyond the hill radius, they end up getting flung back and eventually colliding back with that planet. And you have actually an expectation that you have destroyed exomoons, debris, in some of these cases. I won't get into that as much because that's Brad's work. But also, in the cases where the moons end up going unstable and getting thrown toward the planet, you may expect the moons to are tidally disrupted and form rocky rings. And I try to emphasize these are rocky rings now, right? The rings are actually fragments of these moons, which is different. The picture we have of Saturn's rings, where they're these icy rings instead. And you might wonder, okay, this is another thing that we don't see in our solar system. There's no rocky rings in our solar system. But there was this nice paper a few years ago, which I found pretty, I don't know, it's really interested me. I don't know how well this is accepted in the exoplanet community, but there's this idea that maybe even Mars has had rocky rings itself in the past. And the basic picture is now we have, right, the two moons of Mars. We have Phobos and Deimos, right? And Phobos, the inner moon, is actually getting pushed in right now through the tidal interactions. Okay? And so if you just take that forward, that means sometime in the future, Phobos is going to get tidally disrupted by Mars. And so sometime in the future, probably Mars will actually have rocky rings around it, which is pretty cool to think about. Now, if you actually do the picture in reverse, what these authors claim is this is actually a process that's been ongoing for hundreds of millions of years, where first you have rocky rings, let's say, around Mars. Eventually, through viscous spreading, right, eventually things go out beyond the hill radius and actually bind together and provide, produce some sort of like proto-Phobos, right? So you have a moon here. But that moon, through interactions with the outer moon, gets pushed in, gets tidally disrupted, and you form another ring. And then the same process continues where this viscously spreads, you form a moon, gets pushed in, it gets disrupted. And each time you're losing some mass, of course, from this cycle because you are accreting some of the mass onto Mars. But there's something that actually could happen over and over again when you have these multi-moon systems, where you might expect hundreds of million years with rocky rings and then other periods without them. And so it's interesting to think about maybe some exoplanets are actually going through similar cycles as well that we might find. So anyway, so rings can be important, also important probes of planetary structure, as we've seen by a lot of different work happening even in the theory group at Caltech. So how would we find these rings? To zeroth order, right, we would find enormously large transits because you're going to have this larger, this larger area that's transiting in front of the planet, blocking more light with the rings. And so in his paper in 2018, I thought, okay, great, I'll give some analytic relationships that will tell you for a given inclination and ring properties what the area, the subtending area it is. Unfortunately, I made typos, so I would be remiss to not point out there's an Ono and Fortney paper that came out recently where they found some typos in that. So use that one instead. But anyway, the basic idea is that you have this area here of a planet, but you could also just have this as well, right? Both of these would give you the same transit depth, but they would be very different systems. One has rings and one doesn't. Okay. And so could rings be basically hiding right under our noses as planets that are basically giving you enormously large transits? So what would that look like? So to address this, what we did is basically a Monte Carlo simulation. So basically if you take different populations of ring planets and look at them at all different inclinations like you might expect, what's the distribution of planetary radii you would infer if you didn't realize that they were ringed and not just bare planets? Okay? And so that's what the simulation here is. And so you can see, it depends on what fraction rings, probably not 100% of planets are ringed, right? But you can see what you would expect is some distribution where you'd have your planets going up, and this is only with only rocky planets. I don't have any Neptunes here in this distribution. It's just a distribution of rocky planets. But what you get is this bump from basically seeing some fraction of your ring planets at different inclinations would produce this characteristic bump up here. And I'm not claiming that the Fulton gap is due to ring planets by any means, but this is definitely telling you that if you want to look for these ring planets, basically rocky planets with rocky rings around them like this, they're naturally going to be sort of in this radius range here if you want to look for them. Okay, so that's kind of a, it's not a direct inference that they're rings. We probably want something a little more direct than that. So can we see this through transits? And so that motivated us to start trying to do simulations to actually see what do transits of ring planets look like. And so here's a ring transit here. And so you can see this sort of Saturn passes in front of the star. And if you look very closely, maybe you can see that this is slightly asymmetric, right? It's not a perfectly symmetric transit. And so we can really emphasize this by saying, okay, let's assume this is a bare planet. take what, given what we know from the maximum depth of transit, we can say, okay, what size planet would that be? And then subtract off the difference between a ringed planet and one without a ring, but both subtending the same area. And so if we do that, I forgot the axis. I'll go back to what these axes are, but just look at this for now. You can see there's these deviations where you're getting brighter or dimmer at different times because how the rings are basically interacting with the sides of the star. And so you can really see it here, right? So for example, at this time here, you're actually passing a little more in front of the star than you would if you were bare, and so you're getting a deficit of light. Whereas on this side, when the ring planet is more parallel with the limb of the star, you can see you're actually getting a little more light. And so this sort of characteristic signal would be telling you that there's actually rings there. And you can see roughly, what kind of photometry do you need? It's sort of like 1 part in 100 parts per million. Is sort of what you need to actually detect these ring transits. Okay. And so, we basically explored these more, where now, given the analytic relationships for the rings, we can then construct a whole series of different ring planets. All of these are basically the same area, but they're different size rings and different orientations. And so in this case, for example, these are all the same area. They're all going to give you the same maximum transit. But you can see, depending on the orientation, so theta is basically how tilted it is. Phi, you should think of kind of like the season of how it's tilted this way. For all these different orientations, you can get different characteristic signals from these rings. Okay. So this is one case where we were looking at rocky planets with rocky rings, but then we start getting excited about are there other cases where we might see anonymously like large radii, strangely large radii. Oops, wrong way. And so this is where the superpuffs came in, where we got excited about this. So this is a paper I wrote with Shreyas Visapragada. Of course, he was here at Caltech, and now he's, I believe, at CFA as a Pegasus 51 fellow. So this is a summary table from the paper. I think there's been a couple more now, but of course, it's the usual thing in astronomy, astrophysics. How do you define these things exactly is never quite clear. But you can see, at least the ones I have here that I kind of think about as sort of traditional superpuffs, they're all sort of in the mass range of sort of Neptune-like sized things. You have these radii that are quite a bit larger, though, than like Neptune. Right? Neptune's what is like 3.8 or something in Earth units. And so you combine those together, and you can see here's these densities. These densities are going down, from about 0.3 grams per cubic centimeter down to like less than 0.1. So these are really, like cotton candy planets, right? So incredibly low densities. And there's a lot of weird mysteries about them. So for example, they have if the natural thing is maybe to expect these are fairly thick, large envelopes that are giving you such large transits. But given the proximity of many of these, not all of them, to their host star, you would actually expect photoevaporation to probably remove these envelopes fairly quickly. So it's kind of a mystery how that would work. There's been transit spectroscopy for at least 3 of these now. Or I guess 4, yeah, because 2 are in the same system. And in all cases, the transit spectroscopy, and I'll show you some of these directly, are basically consistent with being flat, which is kind of, unfortunate, right? Because you would think, okay, you have this nice big extended envelope. This gives you a lot of scale height to integrate your light through. This should be like the perfect scenario for getting transit spectroscopy if these are really these big puffed up things. But unfortunately, we haven't been able to see any features in the transit spectra for these things. And so putting these ideas together, we started thinking, exploring the hypothesis, could these superpuffs actually be ringed planets instead? And so let's sort of explore that. What are the implications if superpuffs are actually giant ring planets? And so the first is you can get some idea about what the mass of the rings could be and what the sort of the density of the rings could be. So these are different constraints on what are the ring properties have to be. And so the first thing to remember is because these superpuffs are so close to the parent stars, they can't be rings like Saturn. They can't be icy rings. They have to be rocky, okay? And so that gives you already an expectation of what kind of density of material to expect. But on the other hand, to be so extended, right, they all have to fit within the Roche lobe. And so that means they have to be sufficiently low density material, because if they're too high density, instead they would clump up and end up forming moons instead. Okay? And so using those arguments and using the properties of the superpuffs, we can predict what the density of the material that would make a hypothetical ring out of. And you can see, well, it's not great. You can see some of these, you would need incredibly low density material that it would actually be made out of. So maybe very porous rocks could do this. I don't know. But if you think about normal asteroids and stuff in our own solar system, it would be more like 2 or so grams per cubic centimeter. So I think this is already, especially for this 51 system, it may be problematic. Okay? And then also the rings must be massive enough not to be depleted by Poynting-Robertson drag, right? Because these things are near the host star. There's a radiation field from the star that's going to cause the particles to spiral. And so that actually, these rings last a sufficiently long time, you need enough material there. The real only punchline there is it's not that much material. It's sort of like asteroid amount material. So I don't think that's a real problem. There's also constraints that we can place on the superpuffs themselves, right? So the rings must be fairly oblique to produce these large transits. You can't see these things edge on. You're not going to get the effect we want from that. And this can potentially produce a problem. So the ring orientation, right, these things are close to the parent star, and there's also the tidal gravity of that star that's also going to be pulling on that ring. And the rough way to think about it is where the tidal field of the star dominates over the quadrupole moment of the planet, the ring's going to want to be more in the plane of the star, of the orbit, okay? And that's no good, right? Because if you're in the plane of the orbit, then you're not creating these nice big transits. Okay, so what you want is your planet's quadrupole moment to be large enough to actually be able to hold that ring and hold it in a way that it's going to make a nice big transit. And we know from the gas giants in our own solar system, they're spinning fairly rapidly and they have fairly large quadrupole moments. I mean, you could just see sort of famously by eye, you know, how Saturn is sort of squished down because it's spinning so quickly. And so it's not crazy to have the planet spinning this quickly. The issue is if they're too close to the parent star, they're going to end up getting tidally locked. And if they're tidally locked, they're not going to be oblate enough. The quadrupole moment's not going to be large enough to have the oblique rings anymore. And so what we're plotting here is basically the synchronization time versus the semi-major axis of these things. And so what you can see is, well, it depends on how long you actually want these rings to be around. But in some cases, you're going to synchronize so quickly and have such a slow spinning planet, if it is tidally locked now to that star, that you're not going to be able to keep the quadrupole moment high for the planet and keep the rings at an oblique angle. Okay. And so in some cases it kind of works. In other cases, you can see some of these systems that's not going to work as well. So that's another limiting factor. In all of these, there's also this Hipparchus source. So most of these are Kepler systems. There's also 41378, which we included in the table in our paper, but there was another group that kind of had the same idea at the same time. And so to give them space, we didn't include this in this analysis. But just to show it for you guys here, you can see that this guy is way off. This is a much further system, and so it wouldn't be affected by these sort of effects. So the conclusion on the superpuffs being ring, I wish I could just come in and say, oh, there's this amazing hypothesis. They're all rings. They've just been hiding, as superpuffs. But it's really more of a mixed bag, I would say. They're almost certainly not all ringed. And you could kind of see from the plots there's potential problems with some of the subsets of them with this explanation. In some cases, the superpuffs radii are so large that they can't even be rings, which is pretty crazy, right? That you have a planet that's so large that even if you have very small amount of material in a ring, which basically doesn't contribute any mass at all, it still can't work. And other superpuffs are just too close to their parent stars to have the oblique rings that we want. But I would say, just highlighting this Hipparchus source, it's also known as K293. If I had to bet on any of them, and I probably wouldn't, bet my life or anything, but if I had to bet, one that I think people really should follow up, it's this one, because it kind of has all the different components that are interesting. It's far from the parent star, so all these tidal synchronization effects don't matter. The radius isn't too big, so then it sort of naturally, kind of roughly, asteroid sort of densities would work for the rocky material. It's in a heterogeneous system of planets. So some of these are kind of mysterious because, like, for example, the Kepler-51 system, they have like 3 superpuffs around in the same system, which kind of makes you wonder, because you really have 3 giant ringed planets in the same system. It's relatively old, so things like evaporation probably would have really happened by now. And it's actually a fairly bright star, so I think that makes it, especially for the observers, something that you'd probably really want to follow up on. And then, just to add in, I think Kepler's, if I had to bet for the next one, maybe Kepler-79 is also an interesting case as well. It shares some, but not all of these properties. So what are the superpuffs? So just to be fair, if they're not all ringed, what are the other hypotheses that people are thinking about? One idea that's going around is they're planets that accrete late and at much more than 1 AU, sort of beyond the ice lines, and then they migrate inward. And indeed, maybe they do have these escaping atmospheres, but this helps because you're able to loft all these different particles up from the interior of the planet. And the idea is here is these dust grains that you're lofting up help produce a photochemical haze, which then helps lead to the large inferred radius because you now have this very opaque atmosphere and the flat spectra. And so I think this is an interesting other hypothesis. The question is, how long does this last, right? Especially if you start finding superpuffs that are very old. Does this, how long can this sort of process really continue? But I think, this is something, even though they're a small set of systems, they're such a mystery, and there's so many strange things about them that I think really understanding how they survive will be crucial for sort of having a fundamental understanding of the physics of the masses and radii of low mass planets in the future. And so where does this go next? Like everything else in astronomy today, next is JWST, right? And so, for example, this is a spectrum of Kepler-51d. This is one of these superpuffs. This was taken with HST. And, what can you take away from this? I mean, this is from 2 transits that were stacked together. It's a fairly narrow wavelength range, so, how much can you really see? But this is basically consistent with a flat spectrum, right? As far as like a chi-squared sort of comparison goes. But what if you had JWST looking at Kepler-51? So this is sort of the expectation. So now, just the gray here is the HST data from before. And then for different examples, so this is like a hazy atmosphere here in the sort of orange. Is this one example where we actually have simulated JWST data. And you can just see how much richer it is and how much more you can see. And then we also have comparisons with other things like maybe a water-dominated, a soot-dominated, which is basically a more opaque haze. And then the ring itself, a ring would be roughly flat across this wavelength range. So it's pretty boring compared to these other ones. But with JWST, where you're getting something like, I don't know, like 100, 150 parts per million sort of photometry now, you would really be able to tell the difference between these types of models. And indeed, so I'm a co-I on this proposal that I don't remember that they keep changing the timing, but sometime later in the fall or I think early spring, they're going to be taking these observations with JWST to actually test this. So just to conclude, I hope I convinced you that moons, are important. They could be a key ingredient for habitability for a number of different reasons. And in the habitable zones of M dwarfs, combined, these tidal effects are especially important to understand. The presence or not of moons is an important probe of the exoplanet properties, and tidally heated moons may be especially detectable in the not so distant future. In many cases, the moons are destroyed through tidal evolution, but that's fine as well because now we have rings that we can study instead. And looking for, high radius or low density planets may be the first place to look for find these rings, but it's really sort of this 100 parts per million photometry is where you need to go, which is kind of where things are reaching now. And some of these superpuffs, I probably would not claim they're all ring, but some may be. And I think a few of these sources like 41378 and the Kepler 79d are especially exciting for testing this hypothesis. So that's all I got, so thank you.
Questions for Tony? Tony, if you could repeat the question.
Okay, for the people online.
How does the moon migration depend on the distance from the planet-moon system to the star? And I'm thinking especially about applications for potential moon systems around direct image planets that are very far from the star. They more likely to be stable.
Yeah, so the question was, there's a lot of variables in these sort of simulations of the evolution of the star-planet-moon system. As I move the planet away from the star, how does that affect things, basically? And so the short answer is it basically increases the timescales. So actually, if you just take the Earth, Moon, Sun system forward, the standard story I used to tell my Astro 101 students was that the moon's just going to keep moving until it becomes tidally locked to the Earth, and then it's basically going to stop. But that's not actually true. If you wait long enough, the moon will get thrown in just like this as well. It's just such a long time scale that it doesn't matter anymore, right? That the sun's going to become a red giant and all that stuff's going to happen first. So it's basically just you're going to reach this equilibrium, and the time scale for this instability to come in just takes much, much longer. And it sort of goes with the normal tidal scaling. So it's a pretty strong function of the separation. Answering that question back.
So you mentioned that subtracting the normal planet transit model off of the ring planet leaves like 100 ppm residual.
Yes.
But the Kepler noise floor is below 100 ppm for a lot of targets. So are all of the Kepler superpuffs non-detection for that signature then?
So some of these have been, okay, so the question was, given what I said about 100 ppm sort of residuals for rings, and given Kepler's sensitivity, why haven't we seen these rings yet? And so, I guess my answer is that people have checked, and some of them, they're sort of on the edge. I said 100 ppm, that's like right here, right? But then if you actually want to get enough details to actually measure this, maybe you want something a little more sensitive than that even. And so the studies that I have seen when people did this comparison, they can't rule it out, they can't prove it. It's sort of, a lot of the Kepler data is just right on that border. And so it's sort of the next generation, I think, is really going to solve this better. But you're right, it is it's kind of right at that level, but to get that detail, maybe you want a little better than 100, like I was saying.
Questions?
Is the model you presented purely dynamic, or are you counting for young phases when the planets are just forming and everything's hot?
Yeah.
You might expect different evolution. So is that considered, or are you only doing the dynamic?
So Lynn was asking, am I including the earlier phases where things are hot, things are things are contracting and changing? No, so we're just doing the dynamics, and there are studies where people include those additional effects, and that does sort of can affect stability in some cases, but at least in our framework, we were like, well, let's say all this other stuff sort of settled down and happened. Let's place the moon in now, and then evolve forward. But there could be additional phases, like over the first, I don't know, 100 million years or something, where there's these additional effects as well. It's true.
So when you said internal structure, you just meant density, really?
Oh, I think for the sort of constraining it through the tides, you mean? No, I think there's density, but I think there's also the Q, right? So, and was it, okay, you say that, but the Q for like Saturn, for example, due to the sort of resonances that are seen between the moons and Saturn are very different than the Qs that are inferred for Jupiter, right? So that's telling you something interesting about the internal structure, and especially if you can do something like a rocky planet with a thick atmosphere versus something that has a fairly small core and it's mostly gaseous. I'd expect the Q to be extremely different in those cases, right?
Well, since you bring that up, I'll ask the question that was bugging me. I seem to remember that this turbulent dissipation is very nonlinear sensitive to the Reynolds number.
Yeah.
And so how can you believe any of that?
Yeah, so is Janusz Dewberry here? I mean, there's people in the Caltech department that are working, Jim and the other postdocs and stuff are working directly on this, right? So this is really, I would say quantitatively, I'm not going to get the right answer. But qualitatively, it's telling you something about maybe the integrated Q that you're experiencing over time.
Or just taking you back to Peter's question.
Yeah. So I would say stay tuned, because there's a lot of people that are working on directly that. And it's just like you said, there's stages where you do hit resonances between the modes of the planet and the moon, and the Q can become very small for a little while, for example. And that can affect the evolution. But this is sort of, in this case, because we wanted to look at a wide range of systems, it's more of an average Q that we're really resolving in these cases.
Great, Jonathan. I'm looking for moons that are undergoing strong side effects. You mentioned things that include volcanic species. What about looking for either emission or past effects of footprints on the planet itself?
No, but I think that would be interesting, and including maybe particles being accelerated in radio emission as well, right? So, which I think is something you'd be interested in. So, no, I think all these are interesting options. A lot of cases, it's just there's so many. I thought there was a lot of options when I was doing supernova, and I had to choose the mass of my star. But now it's like you have these dynamical planetary systems, and there's the mass of the moon, and the separations, and the mass of the planet, and the composition of the planet, and there's just so many different variables to work with. So it's interesting to explore, but it's hard to say, okay, how certain some of these things are.
Did you just say supernovae were easier to
Yeah, and then you have this plasma that's just acting nice and easy. You don't have molecules, and so I guess so. The question was how applicable these are. What? I mean, yeah. So the question was, I think, just what range of parameters, mass ratios, these sort of models are applicable to. In each of these cases, we are assuming, for example, that the planet, the center of mass, is within the planet for the moon's interactions with it. If there's a binary planet system instead, it would be slightly different. but I think the main physics holds in all these cases. I mean, especially even in the case of these moons that have been these tentative moons where it's like a Neptune-sized moon and a Jupiter-sized planet. Okay, now the mass ratio is maybe 1 to 20 or something like that in those cases. I don't really see how, the basic framework falls apart there. I mean, maybe we could talk about it. Oh, for those ones. So the question was, some of these moons we found are pretty extreme. If they're all that extreme, why haven't we seen more of them? And so I would tell you to look at the work of David Kipping, who's been on these discoveries. They definitely go through that exercise of, of the statistics of, okay, there's all these Kepler systems. If we put these sort of moons there, what fraction would be retrievable or not? And because you only see them during different phases, right? Sometimes the moon's not always in the right place to actually contribute to the transit, right? And so, but they go through that exercise, and they do have limits on how many of these types of moons could be out there. So I don't remember the number. It's definitely like less than 10% or something like that, because the statistics aren't great. But they do have that estimate.
So I'm thinking about a factor that would be beneficial for habitability in a planet. A magnetic field that protects the atmosphere would be nice. Does the Q value tell us if the core is still molten and moving, or if it's cooled off at all, or is it just strictly what it's?
I'm trying to remember. So the Q value for the Earth, as far as I know, is mostly dominated. So the question was, can the Q value tell you something about if the planet's molten or not? I know, at least for the Earth, the Q value I thought was mostly dominated by the oceans interacting with the floor. And so, at least from that, it's I'd say it's disconnected to that question. On the other hand, right, there have been all these studies, for example, of Mercury and the way that it rotates, and going back to Stan Peele and making predictions based on that of Mercury having a molten core. And so I don't know how that relates to the Q value of Mercury. I can't remember. It doesn't have moons, so I don't remember that being reading about that, but maybe that would be a sort of example case of where there is a relationship there. I don't remember.
Well, suppose we built a 30-meter telescope, or even a
2?
8 one, or whatever you have. What aspects of this problem do you think would be illuminated by having that better inner working angle and the possibility of optical spectroscopy for those systems?
So, just in all these, you saw the spectra themselves, I guess. It's really getting this broader spectra is what you want, right?
So it's the near-infrared spectra.
It's the near-infrared spectra, and in different cases, right? So for this question of the rings versus no rings versus what the heck is the superpuff, I think it would be clear here. I think it's pretty interesting, the secondary eclipses, going back to that and actually understanding if you see signs of a heated moon. And then also in cases where if you can use this to actually do direct imaging, right? If you're not doing direct imaging, you can actually disentangle these different components and then really see things like, oh, now I can actually detect the radial velocity of the planet itself and actually see if it's getting tugged on by, especially if it's like a Neptune-sized moon, that would be, you should be able to detect something like that. So, there's a lot of different things to do. Your job's safe, if that's it.
Well, it's useful to know.